Okay, class. So it's your last AS topic. Last AS topic. Okay, so we will end up with the nuclear physics. Okay, I believe you learned nuclear in your early studies. Okay. You learn about half-life? About half-life, Okay. Now half-life we learn in A2 later. Okay. Here what are you going to learn? In the nuclear physics, we learn about, again, recall back your Rutherford experiment, the alpha particle scattering experiment. We go for it. Then we talk about, yeah, suppose alpha particle scattering. The next we talk about more to, I go make it summary. We go more to what is inside the proton. What is inside the proton? We're going to break, because up to your knowledge, your compile, the smallest particle is what? Proton, neutron, electron. Scientists found much more smaller than the proton. They found proton made of something else. Okay, go to that level. That's what our discussion. Okay. Okay. So first, we're going to talk about first model of atom was developed by J.J. Thomson. Yeah, I believe you heard about him, Thomson. So what is it about atomic structure? Say atom is a positive sphere, embedded on a negative charge is embedded on it. Okay, plum pudding model. Okay. Positive sphere, negative is embedded on it. Okay. Yeah, Thomson is the first scientist who discovered electron. Okay, old technology discovered the smallest particle, electron. Quite funny, but that's the fact. So Thomson discovered electron by using electric field. He burned the metal plate, hit the metal plate. Electron is free. The electron passes through a metal plate, and he found some beam was moving up and deflected. So you see, there is a particle which is negatively charged. With electric field, we know what charge is it. It goes to the positive plate. So this, it goes to the positive plate. So it's a negative charge particle. And then later they name it electron. Okay, electron is the first one discovered. And he talked about this. This is how the atomic structure should look like. But later, what? Plum pudding. But we know we never use this model now. Model has been replaced by Rutherford. Rutherford did a major change in the atomic structure, right? By what experiment? 1909. Gege and Marsden, actually. Marsden, two is PhD students, if I'm not mistaken. Two PhD students did assist. What do you call? You give them a research. So they did that experiment. Okay. Investigated scattering alpha particle by a thin piece of gold foil. So yeah. So they shine the alpha particle through this atom. But what in Rutherford's mind, what model is in his mind is the Thomson's model. Okay. So positive sphere with the negative embedded charges. No free space. So like alpha particle, which is quite heavy, like a lorry, it's a very huge particle with a 4 nuclear number and 2 positively charged, is sent into the atom. The expected majority to be reflected. Why reflected? Because it's totally positively charged. So majority should reflect because alpha also negative positive. But they shocked to see, you know that what happened. What happened? So this is a setup. So they send an alpha per beam with the gold foil. Gold foil is make it as thin as possible, like a layer of one atom. Okay, they make it very, very thin. Okay, so they make it like, imagine like it's one atom, but very difficult to have one atom. But they make it as one atom. The gleaming is like one atom. Then they shine to the gold foil. What happened? Majority passes through. Hit where? The A location. The A is the majority of the alpha beam has been hitted, and maybe less than 1% heated more than 90 degrees. Okay. In exam, they ask, where's the deflection angle? So from the straight line, this like consider as your deflection angle for this beam. Okay. This beam, C, what is the deflection angle from here to the original direction? This is your deflection angle. Okay. So if this deflection angle more than 90, the X is more than 90, about less than 1% of the found. So Thomson model become like a failure. How can majority passes through? Rutherford come out with a model. It's actual observation, of course, is what predicted. 1 year they draw this diagram. They give 3 paths earlier. They ask you to draw the path, how it would pass by. Okay, the first one must go like going up, repelled by the nucleus. Okay, another one is in between, go straight. The one hit the nucleus, the one go to the nucleus. Actually, this diagram is wrong. Sorry, it should be like halfway repel. Nothing touch the nucleus. Electron can't reach nucleus. Okay, only neutron can. Neutron no charge can go straight. Alpha particle positively charged never reach nucleus. No positive charge can reach nucleus. The repelling force very strong. Okay, you see nothing positive charge can go to nucleus. Okay, whatever speed you fire. Okay, so this diagram is wrong. Don't try in the exam. Don't go and touch the nucleus and come out. Halfway, like halfway you shift it back. Then another one is the one going close to the nucleus, deflect more. Okay. 1 year they put like this, the nucleus. I think the beam send is like this, 1, 2, 3 on top. The one quite higher one go little deflection. The second one deflect more. Okay, they want to see that. The third one deflect backward. Okay. This pattern asked in 1 year. Okay. Another 1 year they ask, okay, this one, it goes like this, it come out here. What is the angle of deflection? Find the angle of deflection. So if you extend this and this straight line also, you extend here, then this should be your angle of deflection. Okay, this horizontal line you just make it like a tangent. This line also you make it, this point, the end point also you make it as a tangent. This is your angle. The angle of deflection. Angle of deflection. The more than 90. Okay. Okay, so this is shocking to the world, for Rutherford especially, because majority pass through. So you come out with a new atomic structure. Rutherford scattering experiment, observation, most alpha particle pass through the gold foil undeflected, in a very small deviation. So as a scientist, what do you predict about the atomic structure? How the atom should look like? A big lorry of positive charge going into the atom, and it just come out undeflected. A lot of free space here. So in example, they'll ask, this is the observation, what is the conclusion made? So deviated through larger angle. So this observation, few particles deviated through angle greater than 90. The conclusion made is atom consists most empty space. This one, the undeflected one, we made this. Okay. And nucleus is positively charged. Based on which evidence? The one deflected more than 90 degrees. Okay. A big lorry like bounce back. Okay. That means it must hit a region which is positively charged, as the lorry is helium. And because this lorry is bouncing back, that means it should face a substance, a region where highly massive. Highly massive. Like highly massive, that's why this bounces back, not the nucleus bounces back behind. He is the one bounces back. So the nucleus is said to be positively charged because of deflection more than 90 degrees, and a small volume of high density nucleus is in atom. So you see, there is a small region in the atom which is positively charged, and all the mass of the atom looks like focus over there, called nucleus. For the first time, the term nucleus is used. Okay. So do Rutherford know what is inside the nucleus? No. Nucleus is discovered at that moment. What is inside the nucleus? We don't know. Okay. But because it's positively charged, he discovered proton. Okay. So Rutherford discovered proton. Okay. The second particle discovered is proton. Okay. By Rutherford. Okay. This experiment you have to know in depth. And majority passes through the atom, Wolford. What is the conclusion? Atom consists of lots of free space. Okay. A small portion, more or less than 1%, deflected more than negative. What is the conclusion made? There is a small region which is very massive, positively charged, called nucleus. Discovered. Okay. Yeah. So this is the angle of deflection. I remember. Sorry, I made a mistake. This is the angle of deflection. Okay, not this one, the smaller one. And yeah, this is don't touch the nucleus. Okay, so modern atom now, a neutral atom consists of a nucleus of radius 10 to the power negative 15. This number we need to memorize. Okay. Size of a nucleus is what? 10 to the power of negative 15. Size of an atom is what? 10 to the power of negative 10. 100,000 times bigger the atom size compared to the nucleus. In exam, one objective question or structured question come up. Estimate the size of an atom, 10 to the power negative 10. Sometimes it's called 1 angstrom. One special unit. 1 angstrom, 10 to the power negative 10. The size of the nucleus is 10 to the power negative 15. 100,000 times smaller. So proton. Rutherford model only, proton and electron only. Neutron not discovered by Rutherford. Or neutron discovered after that. I think maybe 10 or 15 years later by who? Chadwick. Yeah, Chadwick discovered neutron. Okay. Why people say it must have a neutral body inside? Because when the nucleus gets bigger and bigger, how can all of them can stay together? Because proton at the nucleus all are repelling. So how can it can still stay together? So later they found there is some sort of another force called what? Nuclear force. Nuclear force. There is a nuclear force. That is one of the strongest force ever on the surface of the earth. The nuclear force is a very short range, only experienced by the proton and neutron. Very short range. That means when they get quite close, strong like a glue. I don't want to say glue. This is super strong. This nuclear force and bond them. Okay, but the proton neutron a little get further, the nuclear force become nullified, totally disappeared. So they split. Okay, when the distance between them get little further, and the nucleus of the size of the nucleus get bigger. That's why more than 85, I think, of what number? Proton number. Normally they are unstable. More than 85. So because the nuclear proton number get bigger, the spacing between the proton neutron get a little further, the nuclear force becomes quite big. They start to split. Okay, so yeah, the nucleus is proton neutron. Protons carry positive charge, neutron carry no charge. Of course, it is all yeah. Not much to say. This all you learned before. Okay, nuclei. It's a nucleus of defined atom whose nuclear and proton numbers are specified. Nuclei. Okay, A and Z. A is what? Nuclear number. Z is your proton number or atomic number. Two names given. Proton number or atomic number. Time is atomic number. But now they use, some schools use proton. Here they use proton number, Cambridge. So atomic number, proton number, same. Top, they call it nuclear number. Or sometimes they call mass number. So all proton and neutron, nuclear number or mass number. Slash is mass number. This is only proton. Proton. Check proton number. There is a proton number. Number of neutron is A minus Z. Okay. Okay, so this you learn this chemistry also. I think I can skip this. 12, 6 proton, 6 neutron, and 6 electron, right? If it's neutral. Okay, so helium is. It's all I think we can skip now. Okay, isotope. So what is about isotope? Anyone? The substance which has same what number? Same proton number, different nuclear number. Physically same or chemically same? Is this the look same? Carbon 12, carbon 14, is it the look same? Or they are chemically same? They are chemically same. They are both are carbon. So chemically they same. Carbon react with oxygen, you definitely get carbon dioxide from both of them. Both of them chemically same. But physically can be different. One might be liquid, another one might be gas. So melting point might be different. Okay, why we learn isotopes here? It's about nucleus arrangement. So I talk about isotope. All the isotopes are, some isotopes could be radioactive. Okay, carbon 12, carbon 14 is radioactive, carbon 12 is okay, not radioactive. So called radioisotopes. Okay, so recall what is isotopes is different number of neutron, same number of proton. 6 proton, 6 neutron, carbon 12, carbon 13, carbon 14. The one abundant on the surface of the earth is just very little, carbon 14. Carbon 12 is the most, 98.89% abundant on the surface of the earth. Carbon 14 is radioactive. Okay. Yeah, so carbon isotopes are nuclear particle elements that contain different number of neutrons, same number of protons. Okay, same number of proton, different number of neutrons. Okay, same thing. This all isotopes like hydrogen got one hydrogen, deuterium, tritium, we call it. It has its own isotopes. And helium also has its own isotopes. Chlorine also 35, 37. Okay. Okay, atomic mass unit. Okay, it's actually discussed in A2. It's U. Symbol is U. Atomic mass unit. Chemistry you learn, right? Atomic mass unit is mass value equivalent to 1/12 of mass of a carbon 12 atom. Mass of a carbon 12 atom. For example, yeah, 1 mole of carbon 12 weighs 12 gram. Avogadro number of atom in it. This is your chemistry. All of you took chemistry from 5, right? So I think this should make sense for you. 1 mole of carbon 12 is 12 gram. This is something for you to remember. Nucleon number is the 1 mole weight of 1 mole of that substance. Okay. Helium is what? 4.2. So nucleon number is what? 4. So 1 mole of helium is 4 gram. Okay. Shortcut, remember. So therefore, 1U found to be 1/12 of that carbon 12. So this is a 1U value. In exam, they won't ask this number given in your front page of your exam paper as a constant. You need to remember. It's atomic mass unit. For AS, you won't be using it. They might ask the definition of what is atomic mass unit. That you remember. Okay, 1/12 of carbon atom. The mass of 1/12 of the mass of a carbon atom. Carbon 12. Okay. Yes. Okay, nuclear reaction. And when nucleus explode or nuclear when break into a new substance, like uranium convert to new substance, okay, nuclear change happen. What are the things conserved? These are the 4, what do you call, quantities are conserved. Do you realize this in your Form 5? Proton number is conserved. when you make an equation of a radioactive substance, your product, reactant and product total proton number, the bottom number must be the same. If A equals to B plus C, I think A is 30, B and C together proton number must be 30. You know that, proton number is conserved, nuclear number also conserved. Top number on the left, product, reactant will be same as all the nuclear number of the product. Okay. Do you realize momentum is conserved? The nuclear reaction momentum is constant. Okay, it means what? You have a daughter nucleus. Let's say you have a parent nucleus of uranium. Suddenly, it give out alpha. Then the new nucleus form, which is the daughter nucleus, will move back because alpha has a huge momentum. So the daughter nucleus will move back. Okay. So momentum have to be constant. Momentum before should be same as momentum after. Momentum before is how much? 0. Momentum after also must be 0. That means momentum of alpha must be same as momentum of the daughter nucleus, correct? Conservation. So momentum is constant. Okay. There is one year they asked past year. They said there is one uranium. Suddenly they put this uranium under cloud chamber. You heard of cloud chamber? What is the use of cloud chamber? Region to see the any ionized particle coming out. How do you know that? You can see a track, right? Track forms because the air is fully saturated. When the ion particle comes out, the air will condense on top of the track, the top of that particle, so form a track. Okay, each track is very thick. Alpha, beta, gamma. Alpha track is thick, and beta thinner, gamma even thinner. Okay, so let's say they put 1 year they asked this question. Uranium was placed in the cloud chamber. They view from the top. Suddenly, 2 track form. One track is to the right, to the left. Another track form like this. Okay, so they found daughter nucleus move here. They found something. One ray moves here. Maybe alpha or what, you know. Okay. So this type of movement, is it momentum constant? What the scientists should predict? Yeah, that's good. There is one more of particle moving here. There is a third particle should moving here because momentum definitely constant, no doubt about that. But it can't see in the track. Why can't see in the cloud chamber? Why? This particle maybe don't have charge. Later they found is this like neutrino, something new substance lah. So momentum is used to find and identify a new particle which cannot be detected in the cloud chamber. Okay, so momentum is constant in the nuclear reaction, and something very new, something contributed by who? By Einstein. It's by Einstein saying that E equals to mc squared, famous science formula. Okay. E equals to mc squared. He is the first scientist says what? Mass and energy are 2 different forms of the same substance, same entity. 2 different forms. You see, mass and energy is mass can convert to energy and energy can convert to mass, and it only happens in nuclear stage. And macroscopic level, you learn about conservation of energy, right? What conservation of energy said? Energy can be created or cannot be created or destroyed. Only can transform from one type to another. But at the nuclear stage, that principle is violated. At nuclear stage, that the conservation of energy never works because suddenly a lot of energy created. Okay, before and after, suddenly energy created is a lot. From where the energy comes out, they found some mass is missing. So mass has been converted to energy. So energy also can create mass. How they found? In the cloud chamber. Cloud chamber they found. They found like the cloud chamber. They found a charged particle which is moving. 2 charged particle, which is colliding. 2 charged particle allowed to collide. Suddenly, new tracks is formed. Suddenly, another 2 tracks is formed here. Okay, no track here in between. So what they predicted, these two particles, which is as mass, they combine, become energy here, some sort of energy particle. Then the energy later comes here, create mass again. Create mass again. So mass change to energy, energy change to mass happens at the nuclear stage. Okay, not at the macroscopic world. Okay, macroscopic world looks like mass is conserved, energy is conserved, but come to the nuclear stage, what is conserved? Mass energy together is conserved. Okay, how much, if 1 gram of nucleus mass convert to energy, how much of energy will be released? E equals to mc squared. Okay, the mass you put 1 gram, c is speed of light, you get lots of energy. Nobody, of course, Einstein's idea all looks weird, like a fairy tale story. Tell a lot of things, but later found to be correct. A lot of things correct. This is something. This is very useful for what you call formation of our universe. Big Bang idea was supported by this fact. Okay. Okay. So mass energy. Okay. If they ask what is conserved, I think the examiner loved this conservation, mass energy. Is something new. Okay, so yeah, this is the nuclear reaction. The nitrogen and helium combined form oxygen and nitrogen. So nuclear number on top must be same, before and after must be same, proton number must be same. At the background, of course, momentum is same, but we can't show in the equation. And mass convert to energy also, you cannot see these numbers. Okay, some mass has been destroyed. When you go to A2 later, you know the 7 nitrogen at the bottom, proton number, the nuclear number 14. The 14 will be in terms of 5 to 6 decimal place. Then only you see some mass has been lost. Okay. So the total nuclear number is constant before after. Yeah. So this all the proton number. This is easy. Okay. One question. Come on. What's that? What pattern of deflection of particle was observed? A few alpha particles were deflected through angle greater than right angle. Yes, a few, of course. Let's we check better answer, B and C, D. So B, alpha particles were deflected from their original path. Not all, some are moved straight, majority undeflected. So B wrong. See, most of the alpha particles deflected through angle of greater than right. No, some right. D, no alpha particle was deflected through angle greater than no. So answer is A. Okay, next. So the fact to be remembered. What is the size typical atomic nucleus? -10, -15, -10 is size of an atom, -15 is size of a nucleus. So what's the answer you can go? A are the closest, -40, -40, -15. Okay. So you must remember this fact. This is a tricky one. Let's see. Think carefully. Think carefully if I give you. The result of experiment provide information about what? Okay, the answer, of course, C or D. Binding energy, binding energy of gold nucleus found out later. Energy levels in electron was who got the energy level? Who said electron got lots of energy level? Which scientist after Chadwick? Bohr, Niels Bohr. Niels Bohr used quantum theory to find that. So Rutherford don't know at that moment. So either C or D. So which is the best answer? C, size of gold nucleus. You never go for structure of gold nucleus. Structure of gold nucleus means what is inside the nucleus. Never discovered. So size of gold nucleus only discovered. Okay, answer is C. Structure of nucleus means what is inside the nucleus. Do they able to find at that moment it contains proton, neutron? No. Okay, so don't know about the structure of nucleus. Okay, last, come on. Come on. So how many neutrons? Just minusing, right? How many neutrons are in the radon and polonium nucleus? So what's the answer, everyone? B and D. Which one? B, boy. So the nuclear number minus proton number, you got the, of course, the neutron number. I think you should know. Okay, next. This also, come on, move up. Okay, let's be second. Okay. So what's the answer? Boy, which is as an isotope, so same proton number lah. The proton number for both of them must be the earlier one how much? 92. So this one also must be 22 lah. So boy, okay. Okay, I skip this. This is so which one is the isotopes? Very fast. X and Z. Okay, X and Z. Okay, this is something different. Okay, one isotope. This is a structured question. What is the answer? Number of proton is 23. Okay, number of neutron is 56 minus 23. Okay, you can get it. Next, yeah. What is the technique? If you find the mass, okay, this is another method. Find the mass of what? Mass of one nucleus of iron. Which contribute mass? Nuclear number or proton number? Of course, nuclear number. 56 gram we know is for 1 mole. Or divide by Avogadro, you can get the one mass of one nucleus law. Okay. Or you can do another step. The 56, the nuclear number multiplied by the atomic mass unit, the 1U. 56 is actually said to be 56U, actually. 56 times U is 1.66 times 10 power of negative 27 kilogram. You will get the mass of one nucleus. Okay. That means helium, right? Helium 4-2. What is the mass of one nucleus? It's actually the nuclear number 4U. Call it 4U, 4 times U. U is atomic mass unit, which is 4 times 1.66 times 10 power negative 27. You get mass of one nucleus in kilogram. Okay. So, or you can think 56 gram is 1 mole divided by Avogadro constant. Also, you should be able to get. Check, do you get the same answer? These two methods. 56 gram, 1 mole, 1 mole is Avogadro constant is how much? 6.42 times 10 to the power of 23, right? Okay. 56 divided by 6.02 times 10 to the power of 23, get the answer. And 56 times 1.66 times 10 to the power negative 27, you get the same number. How much you get?
The same number but different power.
Different power. Oh yeah, one is kilogram, another one is gram. How different by 3? Oh yeah, 1 gram, 1 kilogram. 56 gram divided by Avogadro constant, you get in gram. 56 times the atomic mass unit, which is in kilogram, you get kilogram. So then number is the same. So both technique is used, okay, to calculate your mass, but I think the examiner prefer the second method more. Okay, so use the second method. Okay, so I hope you find the mass. Okay, how to find the mass, get the idea. So now, next question, what do you do? Find the density. How do you find the density? The mass you got divided by the volume. How do you calculate the volume? What formula? As we assume the nucleus as a sphere. So, what is the volume formula? 4/3 pi r cube. Yes, 4/3 pi r cube to be used. So r is the radius, given dash the diameter, divided by 2 and subin. Yes, get me the answer. Come on, this is get the mass, get the density. Something important to be shown here.
Um,
911 density. 911 kilogram per meter cube. Is it? 911 kilogram per meter. I think it's quite small. Yeah, let's get the same number. 911. So mass of the nucleus, divided by the volume. Volume. Okay. Yeah. 2.74 10 power of 26. This makes sense. Because the most dense material in the world is, in the microscopic level, is nucleus. It is the most dense material. Okay. Macroscopic, diamond. Never been diamond. The density. So come to the microscopic stage, nucleus. So 2.7 makes sense. 10 power negative 26. Okay, now, yeah. So now this is the one you have to think. What is your answer, do you think? Normally, this is where the A star student, last part, comment, explain. Yeah. An iron ball is found to have a density of 7,900, but the nucleus of iron is so big. So, by reference to your answer in B2, suggest what can be inferred about the structure of an atom of iron. Yeah. The nucleus density is so huge, but the iron ball's density is so low. Yes, mostly empty space. Because the atom consists of mostly empty space because the volume is huge. Volume found to be huge. That's why density drop a lot. Nucleus density is that much, but when it comes to atom, the density drop means the volume has been increased a lot. Okay, that means got a lot of free space. Okay. So the density decrease means the volume increases a lot. So therefore, a lot of free space contribute to the increase in the volume. So that's the direction of this question. One pass here. Is this one pass here? About 7 or 8 questions, 8 marks. Okay, so that's the first part of the topic. Okay. Okay. Next, we're going to talk about is radiation, reactivity. So far, we talked about nucleus. We never talked about stability. Now you're going to talk about stability. Okay. So stability of a nucleus. What makes it stable? When it has a strong nuclear force. When it has a very strong nuclear force, less proton numbers. Why nucleus cannot be stable? When it becomes not stable, when the number of protons increases, a more stronger repelling force than the attractive force, so it splits. Okay, what force try to split it? Electrostatic force, the positive repel. What force trying to hold it together? The nuclear force, strong nuclear force. So why nucleus cannot be stable? Because when the number of proton increases for a nucleus, the repelling force gets stronger than the attractive force, therefore become unstable. Okay, and the proton number increases, the repelling force, which is what type of force is that? Repelling force, which is the electrostatic force, become greater than the attractive force, which is the nuclear force. The atom become unstable. The nucleus become unstable. Sorry, not the atom. The nucleus become unstable. Okay, next question. How do they become stable? Are they really stable? So the big nucleus break into smaller nucleus and achieve more stability. But are they really stable? No, they're going to break further. Okay, so where are they going to stop? What is the most stable nucleus in the world? Anyone? General knowledge, maybe. What is the most stable nucleus ever found? That means, you know, in your chemistry, in your reactive series, what is the most stable element? Gold. Gold is metal, under metal there. But in chemistry, stability means what? That means it never becomes rust, never loses electron. Okay, stability of atom, right? But here talking about stability of what? Stability of the nucleus, you know. Chemistry, we never talk about changing nucleus. Here we are talking about nucleus is changing. That means you buy today 1 kilogram of gold, let's say 1 bar of gold. 1 billion years later, it won't be gold anymore. You're going to convert to other substance, another nucleus. That's what scientists say. Every nucleus is going to transform to achieve very stable form. The most stable nucleus form ever found is iron. Iron is the most stable nucleus. Iron man. Iron is the most stable nucleus. Okay, we will do in depth about Na2 later. So, are they really stable? No. The transformation will happen until they achieve most stable element, most stable nucleus, which is iron. The prediction every nucleus is going to transform to, the ambition is want to go to achieve iron. Okay, but there is a long transformation. I think about 15 or 20 transformation towards the end we achieve iron. Okay, but there is an intermediate transformation that happens in between, and lead convert to iron. Lead seems got very huge half-life. The half-life of lead seems bigger than the formation time taken for the formation of our universe. Our universe age around 13.7 billion years. Okay, the half-life of lead is more than 13.7 billion years, it seems. So I think we can't see that lead convert to iron happens fast. So we're roughly going to stop at lead. Okay. By the time lead changed to iron, I think what happened to the universe is a very big question mark. Okay. Okay, how do they become stable? By breaking into small nucleus. Are they really stable? No. They have to transform further to achieve a more stable nucleus. How? Okay, how they can do that? By doing two nuclear process. What is the name? Fission and fusion. Fission done by which type of nucleus? lighter or heavy nucleus experience fission? Fission breaks them into small. So heavy or lighter nucleus experience fission? Heavy nucleus experience fission. Uranium experience fission. Very light nucleus experience fusion. Okay, fusion. Hydrogen will fuse. Yeah. So, and when that happened, yeah, heavy nucleus for fission, and fusion is for a lighter nucleus, but not lighter nucleus. And hydrogen now facing, they never fuse. For them to fuse, you need a very high temperature. Okay, how much temperature required? Million degrees Celsius. Million degrees Celsius. Only happens in the core of the sun. At the core of the sun, the hydrogen are managed to fuse because lots of energy required, lots of work need to be done to fuse the hydrogen because the electrostatic force is quite strong. So quite strong and get closer. So they have to overcome that force. So lots of energy required. The energy only can be produced high temperature, million degrees Celsius. Only at million degrees Celsius, the kinetic energy of the hydrogen rises until they are able to fuse. Okay. Okay, class. So we stop here. So another 1 hour, we continue this. Okay. Bye.